record on this computer, and then I will switch my video to. Okay, can you see the slides now? But let me remove the background. You don't see the slides actually. Now you see the slides.
Yep, we can see.
Yes, great, thank you. All right, so today my goal is to finish up with these with the sources of error. I came in the office this morning and my entire green screen had fallen down. My computer wasn't starting, and it was quite an effort this morning just to get everything back in order so we can do this nicely. So I hope we can finish the sources of error today and potentially start the discussion on linear solvers. All right, so last time we finished off discussing what errors were, how we measure error. We talked about true and approximate error, and in both of those situations, we had defined the absolute, if you want, the absolute of the error and the relative value, and then also the absolute and the relative. I have a little chair over here that should move out of the way. 1 second. All right. So, okay, and then we had the approximate error where we talked about also absolute or just absolute approximate error and relative approximate error. Okay. Now we're going to talk about sources of error, and we're going to focus specifically on sources of error with the numerical methods. Okay. So let's get that started. All right. So sources of error. There are model in any engineering pursuit you're going to do, there will be modeling errors. Those come from the model that you have chosen to solve a certain problem. So for example, if you assume an incorrect drag model in your calculation, you're going to get in a lot of trouble for that. Okay, so that's a modeling error. It's not a numerical error, so we're not really going to be concerned with that type of error. There are programming errors where you can make a mistake in your code, just like the mistake that was done in the Ariane rocket and some of the other examples that we will go over. I'm gonna stand on this side, probably better. Okay, and then there are numerical errors, which is our primary concern over here. Now, within numerical errors, there are also within the numerical error umbrella, there are multiple sources of error or multiple ways that errors can propagate. We are going to list a few of the most dominant over here, and those will be our main concern throughout the discussion and the conclusion of this course as we try to complete this course. First type of error are called round-off errors. I'm going to list them now and go through more each one of them with a little bit more detail. Roughly, round-off error, you've probably heard of that as well, is due to the inability of a computer to represent a number exactly. So typically, numbers on a computer are limited by how many bits a computer can represent. And those bits, think of them as buckets or bins where you can put in digits to represent the number. The more bins you have, the larger the number you can represent, or the more accurate of a representation, the more digits you can capture. But in reality, we have a limited number of bins. So you hear like 32-bit, 64-bit, 128-bit numbers. So there's a limit to the maximum number you can store there. Any number above or below those limits, you cannot represent. So you have to round it, and you round either to the next digit or to the one below, or some other arithmetic that the computer is going to use. This is an example of what happened with the Ariane rocket. There are other examples, the Canadian Stock Exchange, the Scud missile crisis in Iraq in 1991. So all of those were due to round-off errors. There are what's called truncation errors, and again, we'll get specific examples about those. Truncation happens when you have an exact mathematical expression, and then you try to approximate it numerically. You have the exact numerical representation, but in practice, you cannot implement that. So take, for example, the Taylor series. We know the Taylor series is defined. You take any function and you to compute that function, any continuous real function to compute it, you can use the Taylor series, but the Taylor series is an infinite sum. And you cannot do an infinite sum on a computer. Now, mathematically, it is exact. The function f of x is equal to the summation going from 0 to infinity. But in reality, you cannot do that. So you have to only pick a certain number of terms where you cut off those terms. Everything that's left is called the truncation error. And believe it or not, that truncation error shows up in your calculations, okay? And finally, there is iteration error. Iteration error is, and we will see this in the next chapter we're going to cover on linear solvers. Iteration error is essentially due to the difference between the actual solution and the current approximation. Now, as you iterate more, we're going to hear more and more about this word iteration. Iteration typically entails improving an approximation. And as you get closer to the correct solution, you are going to reduce your iteration error. So you can control that iteration error as you approach and if you converge to the solution. So let's go over those one by one. We start with round-off errors. And with round-off errors, like I said, computers can only represent numbers up to a certain finite precision. Everything, all other subsequent digits that you want to represent in a number cannot be represented on the computer, and therefore are chopped, okay, or are rounded, or just a sharp chop. It depends on the computer you have. Now think of the different digits in a number as occupying a spot or a bit in a computer's memory. Now this is not how it actually happens. The number is actually converted into binary and then the binary representation, but we're not going to get into that. But roughly, this is a reasonable representation of how numbers can be represented on computers. So take this number, for example, 0.1546, et cetera, Imagine that each digit is assigned into a bit or a bucket in a computer's memory. And that's how you represent a number. Now, depending on the computer you have, there's a physical limitation on how many bits we can have in computer memory. And that's where you hear the 16-bit, 32-bit, 128-bit, etc. The more bits you have, the larger the number of digits that you can represent on a computer. Okay, so more bits is generally better, but it depends on the calculation you're having. If you're only working with integers, that will still apply to how large the integer is. But if you're working with floating point numbers and you only are interested in like 5 significant digits, you don't need a 256-bit computer to represent that. Okay. So when there are less bits than significant digits that you're interested about, the number is chopped or rounded. Okay, so for example, let's say you only want these 5 significant digits over here. You're going to chop and eliminate all the other bits that you're not interested in. You either round them up, depending on the computer, or there's a direct chopping. Now, this chopping is what's referred to as round-off error. When the number to be represented is larger than the number of bits, than what the number of bits can hold, then we call this an overflow error. If it's smaller, we call this an underflow error. If you've probably seen that in older software, like if you grow up with BASIC or Fortran, we were working with like 16-bit computers, and we always ran into underflow or overflow calculations. That's actually what happened with the Ariane rocket. It went into overflow. Okay. Now, round-off error, by definition, then, is the inability of computers to represent all significant digits in a number. And I'm just reading this off of this definition. It is therefore the difference between the actual value of a number and its rounded representation. So in a way, it's a sort of a truncation error. And in fact, in computer science circles, they call this truncation error. But in this class, we're going to refer this to round-off error. Truncation error, we're going to use the mathematical definition where you take an exact expression and you chop it off and you truncate it, okay? So here, when you chop off a number, we call that round-off. And therefore, the error is the difference between what you expect the number to be minus the representation. So in this case, if you take the full number 0.1546, etc., 448798, that's the correct number you expect, but on a computer it's going to be represented as 0.1546. So the difference is those red digits. Okay. All right. Now, some common floating point representations on computers: 16-bit float, 32-bit, 64, 128-bit. You've heard of those colloquially. You can manipulate those in Python. By default, Python goes to a 64-bit precision. So when you put in a number, you type like 12.1. By definition, that's a 64-bit precision number. Okay, so one more thing I don't have on the slides here, also kind of for your own benefit. The 16-bit precision, we call that half precision. The 32-bit precision, we call it single precision. 64-bit is double precision, and 128-bit is quadruple precision. Okay. In reality, like I said, numbers are actually represented, converted into a binary. There's a bit for the sign. There's a bit for where the decimal point is, and then all the other digits are converted into binary, and then you assign the binary bits to the computer. So now we're gonna do an example, okay, with Python, and there is a Jupyter notebook up on Canvas. Before you go ahead and download that and put it on your Jupyter Hub, let me just describe the problem we're gonna solve together. So we're gonna take the number 10 to the minus 5. Okay, so if you add up this number 100,000 times, okay, if you add up this number 100,000 times, what should you expect the answer to be? The answer should be 1. So 10 to the minus 5, 10 to the 5 times is identically 1. So we know the true answer, okay, for that. Now, what we're gonna do, we're gonna use a computer to represent the number 10 to the minus 5, okay? And we're gonna add it 100,000 times and see if we get 1, or what else would we get. And to drive the round of error point even more, we're gonna represent 10 to the minus 5 as a 16-bit, 32-bit, 64, and 128-bit number in Python. We can do that and add each one of those. So we're gonna add the 16-bit representation of 10 to the minus 5 100,000 times and see what we get, etc. Now, here's where critical thinking is. Critical thinking analysis comes in. What would you expect to happen with the error or with the final answer when we use 16, 32, 64, and 128-bit? So take a minute to think about that. Which one of those answers is gonna have a smaller round of error or a higher round of error based on what we discussed? If there's a volunteer, please just speak up.
I would think that the 128-bit precision round off error would be smallest because it has
why?
Because it has the most in the computer that I can store.
Yeah, so 10 to the minus 5, just like any number, it looks benign, but the binary representation is pretty large, right? So there's like 0, 0, 0, 0, 1, 0, 1, 1, whatever, right? And so to represent that number, you need to occupy some bits. On a 16-bit register, you only have 16 bins, 16 digits to capture out of that 10 to the minus 5. So the round of error in 10 to the minus 5 is relatively larger than the 32-bit. Now, in and of itself, it's not a big deal. The round of error is probably really, really insignificant if you do it once. But when you add it 100,000 times, you are compounding that round of error. So you take that error and you multiply it by, so essentially 100,000. Okay, so you amplify this error. So suppose that the error was 10 to the minus 6, the round of error. Suppose it was 10 to the minus 6. If you add it 100,000 times, then that error is going to become 0.1, which is very large compared to the number 1. Okay, so let's see what happens in practice. You go ahead and download the notebook. It's going to be called Round of Errors with Gaps. It's under Python Notebooks and Files. And just to show you here how I'm representing, how we can represent the different numbers in Python with different precisions, we are going to import the library called NumPy. and as NP. And then from NumPy, we're going to call a function called float 16, float 32, float 64, float 128. And that function takes an argument, a number, and returns the 16-bit representation of that number, or the 32-bit representation, or the 64-bit, etc. What I'm doing here, I'm declaring x half. Okay, let me see if I can point my hand correctly. So I'm declaring x half to be equal to the 16-bit representation of 10 to the minus 5. And then I'm going to take that x half and add it 100,000 times. Okay, so x half plus x half plus x half plus x half. We can do this with a for loop. So go ahead and let's get started on the activity. I'm going to switch my screen over here. Yes.
Just to double check. So for the 16 bits, you only get 16 of those binary zeros and ones.
Well, almost. You still need room for a sign and a room to assign the mantissa. So you lose 2 digits just to identify a decimal point and the minus sign. So you really probably only have 14 bits left to represent the number. Okay, but yes, you're right. So you only take a portion of that number. Okay, I'm gonna switch my screen right now. Can we go to the Zoom meeting and FaceTime camera. Okay. Okay, so I'm gonna open up while you work on that example on that notebook. Please just get started working on it. It should have the gaps in it. Localhost. Of course, I need to get my. So again, download it. You probably want to upload it to your Jupyter Hub, or locally just put it in the your Jupyter Hub folder. Okay. I'm having significant technical issues with my computer. I brought my son to the office the other day, and he was playing with the keyboard, and then the computer stopped working after that. So go ahead and get started on it. Just try to develop the code. I will start my timer over here. Okay, can you see my notebook now on the shared screen?
Yes, we can see it.
Great. Okay. So, okay, so what I have here is just essentially the basic code that you're going to be running. And what we want to do to solve this problem, okay, so we expect the true value to be 1, but due to round off with each representation, as you add that number, you're also adding the round off error, right? So you're going to get an answer, you're going to amplify that round off error, okay? And as I mentioned in the slide, we are first going to declare the 16-bit, 32, 64, and 128-bit representations of 10 to the minus 5, okay? Next, we're gonna define a variable for each result. So we're gonna have a result for the half precision. We're gonna have another result for the single precision, another one for double, another one for quad. And that's what I put here, okay? I declared those variables over here. Now I initialized them to 0. Why? Because as we mentioned last time, we're gonna use those as a bucket to add up the numbers. So we're gonna start with 0, and then as we add, you know, you don't wanna offset that addition, okay?
Yes, sir.
Yes,
Uh,
Jacob.
on the first section, it says X double, X triple. Should that be quad or what's?
Sorry, you're right, X quad.
And then in the
yes,
in
good
the
catch.
hashtags over there, it says define half. Those all represent the single, double, and quads.
Oh, that's fine, yeah.
Okay.
Yeah, define single. That's what happens when you copy paste and don't edit your comments, okay? So that was on purpose so that you can catch me in the act, okay? Double. Hey, you can do that when you become a very seasoned programmer. You know, it's okay to make mistakes in your comments. Quadruple precision. Okay, thank you for catching that, Jacob. Good catch. Okay, but the intent is still clear, I hope, that these are different, each variable is gonna contain the different number representation. Okay, we're done with time, let's get started now. Here for this for loop, I hope it's clear what this for loop is gonna do, right? It's gonna add each of those numbers 100,000 times. So what do you think the range is gonna be?
100,000.
Yeah, so okay, I got both Abby, Hayden, yep, 100,000. So 100, 1, 2, 3, 100,000. Good catch. Clear? Any objections? We're just gonna add
100,001 because don't we want it to add up to 100,000 times?
No. So Braden, the counter, remember, starts from 0. Okay. So look at this. For I in range 10, print I. What are you gonna get? You're gonna get 10 entries here. 0 to 9, it's 10 entries. So you looped 10 times. You repeated the calculation 10 times. So doing a range 100,000 times, it doesn't matter if it's starting from 0 or whatnot. What matters in this case is the number of times I'm performing the addition.
Oh, because
Okay.
you're going 0 plus 1 plus 2 plus, okay, I see my error.
All right. No, again, this is a counter. I'm never using I in the calculation. I'm using I here, it's just a counter. Okay, it's just a counter. It's just a for loop. I'm not even using it. All right. So now we're gonna start adding each one of those numbers and put it in the correct result bucket, right? So what do we got for result half precision? What are we doing here? So we wanna add X half precision, but add it to what?
Add it to result half?
Yes, that's correct. So what Sami is suggesting is we do result half equal the previous value of result half, which was our initial bucket. So that's our bucket for half precision. It's called result half. So we're gonna take whatever is in result half, and what are we gonna add to it?
X half.
X half, correct. Is this clear? So think of this, it's not a math equation. It's not A equal A plus X half. It's the new result half bucket equal to the old result half bucket plus X half. So we're just adding, we're just throwing in the X half representation. All right, the rest should be clear. What do we do for result single?
The same thing.
Result half?
Be result
Well,
single.
but single.
Yeah. Okay, so we're gonna do result single plus X
Single.
single, correct. Okay, and result double plus X double, and result quad plus X quad. Agreed? All right, so now we need to calculate the error committed in each calculation. Now, which error am I referring to over here? What is the definition of what error are we calculating?
round off error.
Okay, round off, but which one is it? True error, approximate error,
Relative to
relative,
error?
It's relative.
relative true error. Okay. Who said that, Dylan?
I said that.
Yeah.
David Zoo.
David, sorry, I cannot.
Oh, sorry, I turned off my
see.
camera.
It's hard for me to see who is speaking. Okay. Okay. So relative true error. Why?
Because relative to we wanted it to be relative between each one of our, like, to each one of our results we get. So we take like our previous one, or I don't know how to describe this.
No, that's incorrect. So there are two aspects. You said relative and true, correct? So you're saying true error. You want to deal with the true error rather than approximate error. Why and why not? I agree it should be the true error, but why or why not?
Value is known.
Okay, who said that?
That was me, Sydney.
Okay, Sydney, can you elaborate? Yeah, it's the value. You actually don't need to elaborate. We know the true value. We expect this to be 1. Okay, so this is one of those examples where, although the true error doesn't make sense in reality, but it's illustrating a point in numerical methods, right? So we know the true value to be 1, and we're going to hold our numerical method, which is adding on computers, we're going to hold that accountable to the true error. Okay, so are we comparing half and single and quad to each other or to the true value? We're comparing them to the true value. Each one of those, we're going to compare it to the true value. Now, what would you use here? Would you use the absolute true error or the relative true error? In this particular,
this one, wouldn't we want the relative true error, because we want to compare the respective error between each 16-bit, 32-bit, 64-bit, and 128-bit to see, so we can visually see how 128-bit is, quote, more accurate than 16-bit.
Yeah, that is correct. Now, in this particular example, because the true value is 1, it doesn't matter whether you use true error or relative error or relative true error, because the denominator is 1. Okay, but if we were adding this 200,000 times, right, the true value is going to be 2. Then yes, we want to do the relative error, but that's correct. Okay, so let's see, how do we define then E half, the error committed in the half precision? I'm going to take an absolute value of
1 minus result half.
Correct. 1 minus result half. That's true value minus approximate value over true value, which is 1, right? Now, what about the other ones?
I mean, kind of the same thing,
Yep.
right?
Yep. Result single, and then result double, and then result quad.
Would we be deducted points if we didn't do the absolute value in this case?
What do you mean, like in the homework?
Yeah, in a homework example. If
In the
you were
homework, you have to justify what you use. If I tell you use the absolute, I will typically try to. There's no way to anticipate what you all are going to do. Okay, but I try to be as specific as possible. So I will usually tell you use the absolute relative error, or but in this case we want to use the absolute value because I'm just trying to quantify the magnitude of the error. I don't care if it's over or under. I just want to quantify the error. But if you interpret your results correctly, I'm not going to take points out of this. Okay. If you say, well, this error is larger, and the 128-bit overestimates the number, for example, that's additional information. Now, what I got here is just, now we forgot to multiply by 100, okay? Okay. Oops, I got into an error because I didn't run NumPy over here. I'm running NumPy, importing NumPy, and then I can run this, and look at that. Indeed, the error committed with the 16-bit representation is 0.13%. That's significant. Okay, for the 32-bit, it's 10 to the minus 6. With 64-bit, 10 to the minus 10, and with 128-bit, it's 10 to the minus 13.
Professor,
So you
I
can
have a
see,
question.
yes.
It says for when I try to run it, it say attribute error module number has no attribute float 128. So I'm not sure is that
getting that same error.
yeah.
Are you on Jupyter? Are you on CHPC?
I'm using
or on
the
your
local
local
host. I'm using
Yeah, so you
localhost.
got to update your NumPy. There's
Oh, so it's
something
just NumPy.
off. There's probably an old NumPy that doesn't support 128, or your computer actually does not support 128 bits.
Okay.
Okay,
So if that pops up in the homework, then
it's not
How
gonna
can
pop
we-
up in the homework. It's not gonna
Okay.
pop up.
okay.
All
thank you.
computers now can support 64-bit, so we'll be sticking to 64-bit.
Okay,
Okay.
thank you.
Again, I cannot anticipate all the errors you're going to get. If it's something that is outside beyond your control, like, you have access to that's why we put the Jupyter Hub. So, so try to do it on the Jupyter Hub, but, if something beyond your control, then we can talk about it, okay? But again,
why did we divide over 1?
because that's the relative error, okay? So
it could be
value
2 or
it
whatever.
could be 2 or whatever, right?
Okay.
So then, in your homework, I might ask you add this 250,000 times, right? So that you get the number 2.5, right? So, and then you will see how that error is amplified. But the point here now is that, yes, this round-off error is a big deal, okay? And it can change what you expect in a calculation. All right. Let's continue with our slides. I'm gonna slideshow in window, and then I'm gonna switch my camera to my OBS camera. Okay, great. It's always fun to see your reactions when in person. It's more visible. Everyone's like, huh? I was adding 10 to the minus 5, and then it caused an error, because 10 to the minus 5 is not really 10 to the minus 5 on a computer, okay? So it's always fun to see everyone's reaction in that case. Okay, so Keynote, all right. Now we're back in business. Okay, next we're gonna continue with the example for round-off error in real life. I already told you about the Ariane rocket. Next is an actual homework problem you're going to get on your next homework assignment. So round-off errors can indeed be a big deal. And one of the biggest examples that had papers published about it is the Patriot missile crisis in Iraq in 1991. Now, if you're not familiar with the Patriot missile system, it's an air defense system against ballistic rockets that are, trying to attack a, enemy is attacking your military base or civilian installations for that matter. So it's a pretty smart system. It's got a bunch of rocket batteries. So you're fighting rockets with rockets. So you see a rocket coming. If you can detect the rocket that is coming, you can shoot it with a rocket. Okay, that's the idea. However, you need to be able to detect an incoming rocket. So roughly it works like this. You have a bunch of rocket batteries distributed ideally in a circle with the redundancy. So you have multiple batteries back to back, and then they spread over a circular area. Maybe if you're surrounded from all directions or from one direction, you put a bunch of batteries, and then you have a bunch of radar detection systems. They continuously scanning the sky for objects, because you might be having multiple rockets coming in. So you need multiple radars. And then all of those radars send that information to a control center where there are humans or computers trying to interpret the incoming rockets, okay? Trying to interpret the incoming unidentified flying object, Okay, there's an actual picture of the battery with the rocket being launched from it. Now, on February 25, 1991, this is taken out from Wikipedia. An Iraqi Scud missile hit the barracks in Dhahran in Saudi Arabia, killing 28 soldiers from the U.S. Army's 14th detachment. Okay, a government investigation revealed that the failed intercept. So ideally, what would have happened? The Scud missile is flying. The Patriot system should just shoot a rocket, shoot the Scud, and destroy it. And that system had successfully shot down hundreds of Scud missiles. So the Iraqi military was shooting at the U.S. installation, throughout the war all the time. But the Patriot system was successful in shooting them all down, except for this one. And it was a tremendous disaster, cost the lives of a lot of U.S. service members. And an investigation, however, showed that this was caused by let me get out of the way. This was caused by a software error in the system's handling of timestamps. So the Patriot missile battery had been in operation for 100 hours. Now think of this 100 hours as the 100,000 times we added our round of error. So if at every clock cycle where you are trying to detect a missile, you're committing a round of error, that is going to add up. So see what happens. It has been in operation for 100 hours, by which time the system's internal clock had drifted by 1/3 of a second. Due to the missile's speed, this was equivalent to a miss distance of 600 meters. Now, 1/3 of a second might not seem like a big deal, but for rockets that are traveling at sonic speeds, that's a big deal. In 1/3 of a second, they can traverse maybe a kilometer. Okay, and this is exactly what happened. So the radar system had successfully detected the Scud missile, but predicted where to look for next. However, the timestamp of the two pulses where it was going to detect it and see where it's going to be next, they were being converted to floating points differently. One correctly, and the other one was introducing an error proportionate to the operation time. So that's like the round of error where we added 100,000 times, caused by the truncation in a 24-bit fixed point register. In the homework, I'll give you the details of how to actually calculate that error and predict that the Patriot was going to miss the Scud. Anyway, as a result of the difference between the two pulses was wrong, the system looked in the wrong part of the sky and found that there was no target. No target, the initial detection was assumed like, oh, there was maybe a bird or something else, and then the disaster happened. Anyway, so that's real life stuff. Okay, a round of errors are real. All right. Okay, other disasters due to round off. There's the Patriot missile we discussed, the Ariane 5 rocket that we started our discussion with, and the Vancouver Stock Exchange. It chopped the tracking index to 3 decimal points, producing a loss of 500 points in the index, which is really not true, but it was just a completely silly numerical error. There's a website dedicated to round off disasters that talks about this. It's quite interesting. Okay, so the point though, should you worry about round off error? Not really, and especially not with kind of modern programming where you're not playing around with some of the old legacy software. You had to convert between different precisions. It was weird. You've taken an old software, put it on a new software, and especially with systems that there's a lot of bureaucracy. They want to keep the legacy software. They cannot get rid of the software without calling the president, etc. So it adds all of that, all of those issues. With modern software practices, you're dealing with a variable. You don't mess with the type of that variable. You're going to be okay. But sometimes there's going to be a conversion. We might see this as we move forward in class. But you got to be careful about those conversions. Okay. In general, you don't have to worry about round off error. Most engineering and mathematical systems tend to cancel out round off errors and wash it away. The type of round off errors we saw here, those were really human caused round off errors, right? But if you're not causing a silly error like this, doing the wrong conversion, typically round off errors are not a problem in engineering calculations, because they tend to converge if you refine your calculation. They tend to shrink to 0 as you refine your calculation, okay? So in the absolute, don't worry about round off errors, but don't do silly things with numbers, okay? Converting between bits, etc. If that's not the intention. However, don't blindly trust numbers just because the computer returned the number to you. Be critical about the numbers you see. All right, truncation error. Like I said last time, it is the result, not last time, just a few minutes ago. It is the result of truncating an exact mathematical expression. Let's see, next slides over here. Okay. It is the result of truncating an exact mathematical expression for the purposes of computer or numerical implementation. A great example is the Taylor series, okay? The truncated Taylor series we presented earlier is an example of truncation error shows up. And like I mentioned a few minutes ago, is that in some computer science circles, they refer to round-off error as truncation error. Don't be confused by that, okay? In this class, a truncation error is, let me get rid of this over here. Okay, truncation error in this class is referred to the truncation of an exact mathematical error. Iteration error is sometimes the hardest to comprehend, and I define it as the difference between your current approximation and the true solution. In a way, it's a sort of error, sort of like the true error, but you are refining that error, you are refining that approximation. So iteration error tends to eventually shrink as you improve your guess. And let me give you one example for this. The bisection to find a word in a dictionary. So for example, I give you a dictionary that has 500 pages in it. And then I tell you, okay, what page is the word muse on? Hint, I give you a hint, tell you that M is in the middle of the English alphabet, okay? In the Latin, the English alphabet. There's 26 letters, so M is in the middle. What would you do to find the page, to find what page muse is on? You know, maybe you could start by opening the dictionary in half, and then you look, is M to the left or to the right of what I opened? Then you repeat, you open it in half again on whichever side, and then you say, okay, is it going to be on the left of the half or on the right of the half? And then you take the half and so on and so forth. And that's an iterative method. Someone else might say, well, some of the letters are skewed to the first part of the alphabet. So I'm going to start with 1/3 of the dictionary, for example, or 3/4 of the dictionary, right? And because there's more words in the initial alphabet, so muse is probably further to the end. There's a lot of words before it, something like that. But as you refine, you're gonna converge to the solution. Iteration error is therefore then defined as the distance between the true solution and where you're currently at. But it tends to shrink to 0 or to whatever final best approximation you can get. Okay, we will see a lot of this in iterative solvers when we hit linear solvers in the next chapter. Okay, and then this is the example that I just described. Okay, so let me open the slides again. Please slideshow in window. Okay. All right, so with this, we complete our essentially easy introduction to numerical methods. Okay, I'm gonna get started a little bit with iterative solvers, linear set of equations. But before I open those slides, I would like to hear objections, comments from you before we move to the next set of next chapter, next story. Okay. If there are no concerns, I am gonna, okay, give me a second. Again, I'm not seeing your chat messages, so please do speak up. Okay. So our next big topic, which is going to take us a few lectures, and it's one of the hardest topics that we're going to discuss in this class, is the subject of linear solvers, which are just methods and techniques that we use to solve linear systems of equations. I was going to start off with a very motivating example, but I didn't have time to put one in this slide, but probably we can do that. I can do that next Tuesday for you to motivate you to study linear systems. However, I would like to get started by asking you a simple question, and that is, what is a linear equation? So this is your first activity. Take a minute and describe this to me. What is a linear equation? Okay. Do we have any takers?
I can give it a shot.
Yes, go ahead.
Isn't it like an equation that only involves like the first power of whatever variable is in the equation?
Yes. Yes. So let me just do one thing. I forgot to pin myself in the Zoom. I hope you you guys are seeing me okay. It's always like so many things to do with this. Okay, now you can probably see me better. I hope that was not an issue as we went through the slides.
For me personally, you just went totally black. Oh,
okay.
Yeah.
You were
Okay.
Now you're good.
Pardon me.
Now you're good.
Yeah, but I probably was showing up just like a small box, and you have to double click to expand my view. Anyway, so okay, your colleague said that a linear equation is an equation where whatever variable shows up in the first power. That's the mathematical explanation. Can someone give me more of a intuitive or physical explanation? So you have a quantity that depends on another quantity linearly. What does that mean?
Just goes like the relation is just like a straight line.
Yeah, yeah. So you know, if one of the quantities doubles, the other one is not gonna go like exponentially high. It's just gonna be scaled proportionally to that other quantity. Okay. Now mathematically, this shows up as follows. Slides over here. Okay, so a linear equation is one where the unknowns show up in a linear fashion rather than being squared or under complex functions. So for example, examples of linear functions, 2x plus 3 equals 0. Okay, that's a linear equation. AY equals C. A and C are constants. Y is a variable. That's a linear equation. 2u equal 5. U is a variable. That's a linear equation. Nonlinear equations show up. You have like squares, square root, exponentials, logarithms, sines, etc. All of those quantities, they just make your equation nonlinear, okay, in general. Now, intuitively, like I said, typically our equations are relations between quantities. And a linear equation says if a quantity depends linearly on many other quantities, as those quantities change, this quantity is going to change proportionally by a constant value. So let's say, you know, to make 10 cupcakes, 12 cupcakes. I've been doing corn muffins lately. I learned that when I was in Tennessee. And so to make 12 cupcakes, to make 12 muffins, corn muffins, I need 1 egg with the mixture. To make 24 muffins, how many eggs do I need? 2 eggs, right? to make 36, I'm going to need 3x, not like square root 1.4x, like square root of 2x, right? So that's a linear relation. It scales linearly, right? So those are linear equations. Now, you've probably accustomed to just a single equation with one unknown and one variable, we'll call it one variable. However, in practice, you could have systems of linear equations where you have more than one quantity related to another quantity or other quantities that are all connected linearly. We use the variables x, y, and z, and x0, x1, x2, and so on and so forth. But as long as the relation between all of those terms is linear, so x, y, or x0, x1, x2, all of the unknowns show up linearly without a complex power, without a complex function, then you will end up with what we call systems of linear equations. Okay, I'm gonna let you go here. Next time we'll start digging deeper into the meaning of linear systems. We'll do an example and look at all the issues with trying to solve systems of linear equations. We're going to talk about systems that have a million equations or a billion equations in them, and how to solve them and what methods we can use to do that. Okay, with that, I'll let you go.
Thank you.
Yes, thank you all. And yeah, I released homework 2 has been assigned, and as usual, it will be due next Thursday. Okay, please keep communicating with me over Canvas and the email on Canvas. I'm been whenever I see a message, I try to respond to it immediately. I saw some people were trying to do a GroupMe or whatever forums, etc. You guys are using. I do not support that, so you cannot get the benefit of the TAs or myself. We only look at the Piazza that is dedicated to this class. Okay, so any other pursuits are your own responsibility, and whatever questions you might get the wrong answer. I don't know what ends up happening in those rooms, but there's no way we can control the conversation over there or adjust the veracity of the statements happening there. We can only do Piazza. So think about that as you move forward. I'm happy to consider other platforms, but it needs to be approved by the university. Make sure that there are some safety concerns, etc. So, but if you have a suggestion that there's another system that is easier to use and cleaner, do let me know. I'll look into it, and if everyone likes it in the department, we can push towards adopting it. Okay.
Okay, I was just curious about when you are in on demand and you're launching Jupyter Notebook, it asks you to put in the number of hours. Just wondering.
I suppose this is, hold on, I can't see who's speaking. Is this Natalie?
Yeah.
Yeah, so Martin reached out to me and we created an app for you, and I posted that in the front page and I think an announcement. So if you just click on that and click launch, you should be okay. Now, if you run into trouble, like your session dies after an hour, then put 2 hours, but I don't anticipate that that's going to be an issue. But if that's the case, then just relaunch it or change the number of hours. But I don't know what caps they're putting in their system, and typically there is like some automatic back end. You can be allowed to consume resources for an infinite amount of time, right? So you're probably running into that. But I would start with whatever default value, and then if you run into problems, just change that number of hours.
Because I was wondering, because currently I have 2 sort of like sessions open with different times remaining, but if I do connect to Jupyter on either one, it should, like, my work that I did should be the same, right?
Yeah, because the file is stored on the server, and you connect to it, it's gonna load up the most recent as long as you have saved it. The state might be different because one notebook you're running, the other notebook you hadn't run yet, so it's not going to load up the same variables. We got to re-execute it again.
Okay. Okay. All right. Thank
All
you.
right. Thank you, everyone.